Please, Avi.
Thank you.
Hi guys, I'm happy to be here. As you see, I got this free T-shirt yesterday from the Simon Center. Maybe you like it. Okay, so like Luis said, I'm sure you all use computers even when you don't know it all the time, maybe since given your ages from birth. I want to tell you some things that go on inside the computers and outside computers, which are still computations. And it's going to be very informal. You can stop me and ask questions. Maybe I'll ask you some questions. And we don't have to go all the way to the end, because I hope you'll have questions at the end. Anyway, let me start. So, I think, okay. So I like this very old TV series called Star Trek. So it's a story. There is this species of, I don't know, bad aliens called the Klingons, and they have a spaceship. So I want you to imagine that this spaceship has been hovering around our planet for, I don't know, 10,000 years, observing life in the planet, and trying to figure out when eventually it introduces himself, when they introduce themselves to the inhabitants of our planet Earth, they want to know who should they talk to, who is the most intelligent species in the planet. So, you know, they observe that there are very interesting structures on Earth, very impressive structures, and they're impressed, and they seek to understand who built them. And they see that, you know, the first was built by humans. They recognize one species. The second was built by termites. You probably have seen these termite seals in pictures and so on. So they are impressed. So maybe one of these two species is a species to turn to when they land and tell someone, take me to your leader. Should it be a human or a termite? So they know more. They study us very well, and they see that people have some like 100 billion brain cells, and termites only 10,000. And, you know, I don't know, I wonder what you think. I mean, were you an alien trying to think who's more impressive? Would you think the termite is or the human is? Let me do a show of hands. Who thinks the humans are more impressive given this information? All right. And how many think the termites are? All right. Yeah. Yeah, I was also hesitant. Okay. So that's just the beginning of the story. You know, they have all this infrared and whatever equipment, and they look more closely at these structures, and they see that engraved in the pyramid are this sequence of numbers. Anybody recognizes this sequence? Prime numbers, yeah, right. Maybe they see 100 of them or 1,000 of them. And of course, they know all about prime numbers. They are very impressed. And, but they look more carefully, and they see also on the termite field these numbers. So now the question is whether this story stopped making sense or not. I mean, who thinks that, you know, termites can generate the prime numbers? How much? Sure, just say yes. Or, who thinks they cannot? Okay, why can't they? What's lacking? What don't they have? They have 10,000 brain cells. Is this enough to write a program to generate the prime numbers, in your opinion? Yeah. But the answer is yes. It's much less. And that's okay. You get an A for answering. That's a very important point about computation. It's one of the several points I will make that maybe you didn't know or didn't think about. This number of brain cells is far more than is needed to write a program to generate a prime numbers, and for almost anything interesting in math, you don't need much more. In fact, it's enough to write the program running your laptop. So there's a very few bits of memory are required to, to write programs which produce sophisticated outputs. So let's talk about the origins of this understanding. And so computer science, unlike many other sciences and disciplines, we know exactly when it was born. We have a birth date for this field. This is a person who really started it all, Alan Turing, one of the greatest thinkers of 20th century. Who never heard of Alan Turing? That's okay. I mean, yeah, but most of you did. Okay, so I'll tell you some things about him during the talk, starting now. The time, the birth date was in the publication of a particular mathematical paper with this very weird title which has a German word in it and Chandler's problem. So he wrote this article. The article appeared in a mathematical journal, in the journal London of the Royal Society in England. This is by far the most influential paper of mathematics that was ever written, because this is what started it contains in it the definition, a formal mathematical definition of what a computer is. And here's a picture of it. It's just what should strike you here. It doesn't look like your programming language, but what should be striking here is how simple it is. So a computer is just a very simple device which has a long tape for memory divided into cells in which you put zeros and ones, and a finite state control, some tiny program, maybe with 10 bits in it, running along this tape and reading and writing into this memory. And that's the execution of a program. The important thing is it's a completely formal mathematical definition, so you can do math on it. You can prove theorems about it. That's the beginning of a science, of computer science. And the simplicity of this device and more things which are in this paper, which sort of introduce the beginning of programming, understanding that there is one device like this which can simulate all others, like your laptop program, the operating system of your laptop can run on it, maps and taxes and games and so on. So the idea of universal computation. And together with these ideas and this simple device which clearly calls for implementation, people started building computers. Of course, many other people build computers. I will not talk about it, but this was the formal beginning of this science. That's one important thing about this paper. It's not the only one. Another important point that Turing made and also Alonzo Church made at the same time is that this simple device is actually the most you can, it captures all possible notions of computations you can imagine. Okay, so it can simulate anything else which computes, and we'll talk about the meaning of this a little later. So it's a very bold statement, but so much time has passed since 1936, and nobody yet came up with a way of computing that cannot be simulated by this very simple device. And my last point is that the birth of computer science came with the birth of the limits on what computers can do. So this Chandler's problem was a problem of David Hilbert, the most famous mathematician at the time, who believed that anything provable in mathematics can be computed in a mechanical way. So that is what Alan Turing proved wrong. He proved him wrong. In order to prove him wrong, he needed, first of all, to be able to prove something, so he needed a mathematical device capturing computation. And then he showed that there are some problems. So if you had the notion that computers can solve every problem, this is not the case. There are problems that computers can never solve. One particular one, which is interesting, is the following problem. I give you a program and tell me if there is a bug or not. tell me, for example, if there is an input for which it will run forever and never stop. This is a problem that is well defined and cannot be solved by computers. This is what Turing showed. Okay, so let's talk about algorithms. Not looking at this device, but in layman terms, it's more or less the following. An algorithm, which is, you can think of a computer program, is a step-by-step, simple and local mechanical procedure that always stops and delivers the right answer to your problem on every possible input. It's a mouthful a little bit, but if you think about what computers are doing or what programs, steps in programs you give, there you go into this register, you add it to the other register, you multiply something. Anyway, so that's a general description. And here's an example you are well familiar with. This is an algorithm you learn in second grade or something, long addition. And you know how it works. I mean, I just have it here running, but this is a process that Turing tells you in the paper. This exact computation that humans use was his model when he created the Turing machine. Okay, this is how we compute, and that's how we let the computers compute. It's very local. We keep looking at 1 or 2 squares at a time and move along with the tape. Maybe here the tape is 2-dimensional, but that's, it's not needed. 1 dimension is enough. So the description of this algorithm takes very few bits. We know how it is. We are taught it and so on. It's very simple to describe. I want to stress the contrast between the final description, the few bits describing a program, and the fact that this program can add any 2 numbers of any length. So it solves infinitely many instances of this problem just with this final description. And we'll talk about this more later, about this discrepancy between the final description and the infinite number of inputs. Of course, this is an important part of the proof that some problems are uncomputable. Okay, so these are algorithms. This happens to be a very fast algorithm. The running time of this algorithm is roughly the length of the input, up to some constant, maybe 10 times this. Not all problems are so easy. So I want to talk now about my field of research. It's called computational complexity theory. So what we are trying to understand is which problems are hard, which problems are easy. Or more generally, if you have resources that you invest in your computation, it can be time, it can be memory, it can be energy, it can be communication. It can be various parameters that you care about. How much of them you need to solve particular problems. So we saw that addition, if you look at time, takes this is what we call linear time, just roughly the length of the data. And I want to talk about other problems that some are easy and some are hard, or how do we distinguish with them, again at a high level. So easy and hard problems. I just have 2 examples. The first you are very familiar with, multiplying 2 integers, right? So I have 2 integers. I want to know what their product is. And we learn in school an algorithm for this. It's a little more complicated than addition, right? And in general, if these 2 inputs are not 2-digit number, but maybe 1,000-digit numbers, or in general, n-digit numbers, you want to know what's the time you spend on the computation relative to the length of the data. And in the algorithm we learn in school, you probably remember how it looks like. It's roughly n squared. So it's roughly the square of the data size. Square, this map from n to n squared doesn't blow up much given the speed of computers. Even if you have inputs, numbers to add that are 1,000,000 digits long, it will take a fraction of a second, as you probably know. So this kind of problems where the time invested is polynomial and squared and cubed in the length of the data, we call easy. What are hard problems? Hard problems are problems that, in this example, just the opposite of multiplication. What's the opposite of multiplication? I give you a number, and I ask you to break it into its prime divisors. Okay, so in this number 1541, we saw it's the product of 23 and 67, and each of them is prime, so that's a factorization problem. And people have looked for hundreds of years for fast methods to do this, and today the best known algorithms are not much better than just trying out, in a brute force manner, all prime numbers between 1 and the given input. So it takes exponential time to compute. Exponential time is far worse than polynomial time. Everybody knows the phrase exponential blow-up. What this means is that even if you have a small number to factor, something with, let's say, 10,000 digits, and you run the fastest algorithm known on all the computers in the world, right? This will take maybe 1 billion years or 100 billion years, okay? So what does it mean? It means that we can never factor such integers in general, right? Maybe specific ones we can, but in general we will not be able to do this. So you would like to say that this is a hard problem. We would like to say. The truth is we don't know. And in fact, one of you can come up tomorrow with a fast algorithm for factoring. So we just don't know so far. I should ask you about maybe multiplication. You think there's a faster way to multiply than the one you learn in school? Something that will run faster than quadratic? Yeah, I don't expect you've seen this. But it turns out that there are much faster ways to multiply numbers, almost as fast as adding numbers. But we still don't know if it's quite as easy as addition. But for factoring, we don't have anything that is even similar that runs in polynomial time rather than exponential time. So we don't know this. That's a fundamental fact. And the second is that we will assume that it's hard. So what we are discovering now is another really interesting observation of the field, is that hard problems can be useful. We'll see how it's used. So hard problems, of course, easy problems are useful. All the apps you see in your phones, they come from algorithms that people invented for various things, for navigating in maps, finding shortest paths between, how to drive between 2 points and so on. There are many problems for which efficient algorithms were discovered, and then you find them on your phone apps. But there are other problems you don't find on your apps because nobody else invented a fast way to solve them. So we want to, and you see why, assume that it's hard, and then it will become useful. So I want to talk about this now. So we'll assume this, take it as an axiom for now, that factoring is hard, and see what it gives us. Okay, so what does it give? I want to pictorially capture what we saw in the previous slide in these two examples. Yeah. So on the left and right, you have two pieces of information. On the left, you have two prime numbers, P and Q, given explicitly. And on the right, you have their product. So these two pieces of information are equivalent. If I give you one, you can get the other, right? In one direction, you multiply, in the other direction, you factor. They uniquely define each other. They are completely equivalent information theoretically. It's like having the same word in English and in French. You can translate the English to French, you can translate French. So they are equivalent descriptions of the same object.
Prime factors are unique?
Yeah, prime factors, that's a very good point. It turns out that there's only one way to factor numbers. Thank you. It's a fundamental fact. So, but we just saw in the previous slide that moving in one direction can be done very quickly. multiplication. And in the other direction, assuming that, we said it's hard, but if we don't have time to wait 100 billion years, then it's really impossible. So things that require exponential time are really impossible for any agent, any person, any computer that is, has just a bounded amount of time. So this introduces some asymmetry into this information. This computational point of view puts asymmetry on equivalent pieces of information, which is extremely useful, which I'll show next. But I just want to point out that factoring is not the only, or multiplication, factoring are not the only pair of problems with this property. We have others. We don't have as many as we want, but we have others. But you expect that there'll be more because, in nature, processes that go easy one way and hard in the other way are all over the place. This is just one example that you know. Right? So we should be able to have more examples of such problems that are easy in one direction and hard in the other direction. Okay, so how do we use this hardness of factoring? So the main application is something, again, everybody is living with and through and using all the time, modern cryptography, namely what underlines security and privacy and electronic commerce, everything that everybody uses all the time. So I won't tell you the story about it, but first I will tell you about ancient cryptography. So what did cryptography do for, several millennia until roughly 1975? It was focused on the problem of secret communication. So people always had secrets, and they always wanted to tell secrets to some people, and so that others will not understand them. So this, of course, from James Bond, from spy movies, but it doesn't have to be spies. By the way, in this field of cryptography, some of the protagonists are always called Alice and Bob. So here are Alice and Bob. They want to communicate secretly. And the question is, how can they do it? And in all solutions given until the mid-70s last century, they use some secret key. So somehow they can communicate secretly only because they both have access to the same secret key. They decide on some phrase in a thick book or something that nobody else has. Okay, so that's how they all work. There are many famous examples. This is the famous Julius Caesar code, so from 2,000 years ago, substitution code. And the right is a picture of the Enigma machine. I don't know how many people heard of the Enigma machine. All right, good. So this is, for those who don't know, this is a kind of cipher code that was used by the Germans during World War II. And it's another story about Turing, very important work that he did, which is very different. He and his team during World War II were able to crack this code, being able to break it and understand the secret communications, in particular between headquarters and the U-boats in the Atlantic, which were sinking ships of supplies from the US to England. And Churchill called this success of breaking the Enigma code the greatest single contribution to the victory in World War II. So that's another huge achievement of Alan Turing. Anyway, I want to go back to this secret communication. If you think about it, there's something wrong in this picture. You want to achieve secret communication, and in order for it, you need a common secret key that you could only have achieved if you were able to secretly communicate before. So you are solving the problem by reducing it to the same problem. So there's some, of course, physically can be done. We hide in a room, we agree on secret key and so on, but you would want to be able to do it without having met before. So this is a challenge, and that's the challenge of modern cryptography. So we want to do it without any secret key or knowledge or meeting between the parties. So it's more or less like this. You are in a crowd, like in a room, and two of you who never met would like to start, maybe Alice and Bob here, want to start a secret conversation without having met before and with everybody else listening. Okay, so again, I don't know. You two want to start talking to each other here in the presence of everybody else without anybody understanding it and without you having planned anything before. You think it can be done? Yeah, very good. The answer is yeah. Yeah,
How?
and you know how, yeah.
RSA?
Yeah, very good. So you are way ahead of me. Yeah, so we will talk about this in a second. Yeah, so this can be done. It's extremely surprising that it can be done because the intuition of most people will be that this is impossible. And like you say, many, in fact, do it on a normal daily basis. It doesn't look like that. It looks more like that, right? It looks more like you shop online, so you want to be able to secretly communicate with this online store. And of course, you never met this online store before, right? I mean, you log in and you go to their website. You never met them before. You have nothing in common. And nevertheless, you want to be able to send your credit card number knowing for sure that even if somebody is listening to on the line, they cannot figure out what your credit card number is and cannot use it to purchase more things for themselves. Okay, so this is done routinely, and I'm sure you know that, and many of you know how, like RSA. Basically, I want to stress this, RSA is a particular public key encryption scheme that definitely dominated the security systems in the past 50 years. It's slowly changing. Maybe we'll talk about why. So the secrecy, the privacy of your credit card is assuming the hardness of factoring, is assuming this asymmetry of information between pair of prime numbers and their product. So I assume you knew this too. So this means that, if tomorrow really somebody discovers a fast factoring algorithm, the world economy will collapse in a second. And it is completely possible that it will happen. So one has to protect against it and plan with some other, other functions with the same properties. Okay, so this is possible. Okay, so we are done with cryptography, and what else do I want to tell you about? Yeah, of course, secret communication is just the beginning of modern cryptography. There are many, many things that you can do using this axiom, contract signing, and you can play poker on the phone, on the telephone, without having cards if you have, just assuming this, and many other important cryptographic protocols. But that's the end of this particular story now. I want to tell you now about computation in general. So most people will talk to things that computation is what happens inside computers, which of course is true. I want to tell you in this last part of my story is that computation happens lots of other places, and in fact all over you. So let me explain this. So let's go back to the picture we saw before. So I define an algorithm, a computer program, basically as any process which manipulates some environment locally, very simple rules applied to very local parts of this environment, and just iterate this process. This is what an algorithm does, certainly in a computer. And as we said, it's a final description, and maybe with any starting point, with any initial value and input to this process, it will produce something else. So it can manipulate an infinite number of inputs. I want to claim that there is another algorithm that I'm sure you are familiar with that doesn't happen in a computer. This is DNA replication, right? Where cells divide, they copy the DNA which is inside the cell. So there is an algorithm which just copies a sequence of letters. These letters are these pairs, base nucleotides, the letters that compose the sequence of DNA. So there is a sequence like this in every cell of your body. It's about 3 billion letters long. And every time a cell divides, this sequence is being copied. How is it being copied? By an algorithm. An algorithm is a very simple algorithm. If I ask you to write a program to copy a sequence, I'm sure you'll produce a program with a few lines that does it. Here, it's not done in a computer, it's done in a cell. The operations are not on bits. There are some, the algorithm is embedded in the RNA and some enzymes which are in the cell. But nevertheless, it's an algorithm. It gets an input, a sequence, it produces another copy of this sequence. So an algorithm happening in your cells. And I want to claim that this happens all over the place. You can think about it the same, it will copy any sequence. Not, whatever the DNA is, and of course each of us has a different DNA, is being copied. I want to claim that there are so many places.
It's not twisted.
In the picture it's not twisted. That's another side bonus which we don't. There are many environments in which local interactions produce, being evolved in this way. And you just have to set up what's the environment and what do you call local. Of course, bits in computers are manipulated to create computation in computers. If you have a network of computers, maybe locality is talking to your neighbor, to the neighboring computer on the internet, so sending messages. Neurons in the brain communicate and update themselves. Atoms in matter, bacteria in petri dishes. There are lots and lots of prices in markets between competing companies, or friends on Facebook are evolving the content of this social network and so on. So I want to claim that this happens really everywhere. So computation is essentially any process that I think any human ever defined. And why does it matter? It matters because the theory of computation, computational complexity theory, is a theory which studies, as I said, resource allocations and expense of various computational tasks in computers. But this methodology that was developed in the past 50 or 70 years is useful to study processes in other, other parts of nature and life. And there, of course, as I said, the elements of computing, the steps are different than in the computer, but still they also have their own resources, and I guess evolution took care of the fact that, DNA replication takes seconds rather than a million years. There is an efficient algorithm for this. So there are many processes you can imagine, and they are studied. Of course, they are studied by the natural sciences, and we want to understand them. And I want to just say that you should think of them also as computation, these evolutions of, babies in the womb, or the weather evolution. All of them we have theories for, and so nature computes these products, and we try to predict them. So the theories of nature are trying to predict them again by computation. This happens in mathematics all the time. You learn lots of algorithms to solve problems, for example, solve equations. Also mathematicians who are, thinking about proving theorems are themselves computing something in their brains. There are other things that happen in the brain which are also evolving by some physical, chemical laws. What happens when we recognize people, or when we have an emotional reaction to anything. It's some process that happens in the same way computation happens. It's an evolution of simple local rules. Also, these patterns are generated very simply by, this slow generation of line after line of cells in seashells, and you get really cool patterns. Okay, so my almost last point. I thought that I could not, namely that computation is everywhere. I could not end this talk without talking about AI. I'm not an AI expert, so I want to make sure of this. I just want to tell you about the beginning of this field. Of course, this is probably too small. The way it's taking over our lives is, will soon swallow everybody. So I want to tell you about the beginning of this. And that's another really interesting story. So as maybe some of you know, after World War II, after Turing was done with cracking the Enigma machines, both he and many other people went on to build computers. Right? So these were the early computers developed in the late 40s and the early 50s. But most of these computers were developed for a single purpose. I'm sure you can guess. It was for military purposes, to calculate trajectories of missiles and things like this. There were other applications. Weather prediction was an early application, and also some business. IBM was created then, and some business applications. But I don't know if anybody, except for Turing, which in his early days already thought of the idea that these machines can think. And he didn't just think about it, he wrote several papers. It's a very famous paper in 1950, in which it just tries to articulate what would it mean for a machine to have intelligence. So that's a very remarkable thing about Turing. He was really an amazing thinker. And he was trying to define it. And in this paper, his papers, if you ever get to read them, are extremely eloquent. He asked, how do I define intelligence? And his conclusion is that the best way is to be pragmatic and just test whether something is intelligent. And what's his idea? I'm sure many of you have seen this imitation game, what it became to be known as the imitation game. The way you decide whether a robot or a program is intelligent, whatever intelligent means, is defined by this test. You just let some referee, in his story it's a human referee, interact either with a human or with the robot. He doesn't know which. And he should conclude at the end whether he's talking to a robot or a machine. And if this succeeds for many attempts and for many different referees, you will call the robot intelligent. Of course, this was in 1950. We've gone a long way, and in particular a very long way in the last decade or so. So today we have this AI revolution, and GPTs pass this test easily all the time. Yeah. So I think that good questions to ask yourselves about the future is where is this going to? Maybe this is in some sense answered, but how will they develop? How will AI develop? Will it have some conscious behavior of some? Will it have feelings? In fact, it forces you to ask, in what ways are we different than machines? So let me end with this, leaving you with this, and summarizing some of the points I mentioned. So one thing I want to stress is that in many applications of computers and technology in general, ideas and theory, mathematical theory, came before there was any implementation. In fact, it enabled the development of technology. I gave you two examples. One, the computer revolution itself, starting from mathematical paper, and the second was cryptography, was again developed first as a theoretical science, and then, with the applications of electronic commerce of the internet, became a reality. I told you in the beginning, computers cannot solve all problems. You have to remember that. There are very simple problems computers cannot solve at all. Even solvable problems come in a variety. Some of them are easy, some of them are hard. And so, sort of amazingly, hard problems can be useful, not just easy problems. We should really find out whether this problem of factoring integers is hard or not, because I can tell you that our field has been trying for decades and we don't know. But I want to tell you one short story. It turns out that about 30 years ago, or 40 years ago, there was a suggestion to include quantum phenomena. We have quantum mechanics. You all heard about it, I'm sure. This part of our reality, important part of physics. People suggested integrating it into computers. Why not use quantum phenomena in computers? And it turns out that if you do that, at least theoretically, you can have a model like the Turing machine, you can have a quantum Turing machine, you can define it. And Peter Shaw, in about 30 years ago, discovered that if you have this machine, if you have such a machine, or at least on a theoretical model, factoring integers become easy. And of course, you can imagine that the whole world exploded with attempts to build them. And some of you know about these attempts. We don't have quantum computers yet, so security on the internet is not yet in danger, but of course, people are trying to replace factoring with other problems that are hard, even for quantum computers. And my last point was that computation happens not only in computers, but everywhere around you. And it's important to view it like this, because I'm sure that computation theory will enhance natural theories of nature. I wrote this book. It's more intended to undergraduates than to high school students, but I'm sure some of you can read it or can read parts of it. It's supposed to be friendly. So you can try. It's free on my website. Thank you very much.
Thank you.
So we have plenty of time for questions if you want.
Thanks for a wonderful talk. I'd like to make a little comment. There was a famous computer scientist, Marvin Minsky, in MIT, who gave an answer to one of the questions that Avi was asking, is that he said that humans are computers made of meat.
I would go along with this. I would concur.
You have any questions or comments?
How does factoring specifically relate to the public key encryption? Like you said, because it is hard to factor, we can't decrypt
Yes, so it's a little technical to explain, but you imagine that you have the prime numbers and I don't, and nobody does, and I want to send you a message. So what you do is you publish on your website, or you announce the product of these two primes, okay? And then the way I encode my message, I want to send you something. I want to buy something from you, or I want to tell you I love you, or something. I want to send a message that I don't want anybody to understand. Think of it, this message as a number, right? And I simply square this number, modulo what's called, so I should give the name. The two primes are your private key. The product of the prime is what's called the public key. This is published. Nobody can figure out by our assumption what your secret key is. I don't need your secret key to send you a message. I simply take my message, X is the number, I square it, and I reduce it modulo your public key, which everybody knows. Okay, I send it to you. It turns out that, so what's my message? It's a square root. What is my secret message? It's the square root of what I sent you, right? Computing this square root turns out that is more or less equivalent to factoring this number. On the other hand, if you have the factors, you can take square roots very quickly. So that's how you decipher my message, and nobody else can. This is roughly, standing on one leg, the explanation of the RSA system that was mentioned before. And you can do this whenever you have such an asymmetry between computing one way and computing in the reverse.
Yep.
So you have said before that AI is partially inspired by how the human brain system works, that how the neurons inputs information from the surroundings and how they train and learn those informations. So how would you say the potential development of AI in the future? Would they mimic more about the human brain system, and where would it go in the future?
Yeah, so there are several points you make, and they are all excellent. So one is that this is not discussed so much, but the development AI is going to help us understand ourselves big time. I mean, because of the similarity in design of AI systems built from basically neural networks, or things that look like neural networks. The development from now on is mysterious to me, as I'm sure to everybody else, including to all the experts who are training them. They are certainly getting smarter and smarter, so they can do amazing things that certainly we cannot do, and they're helping a lot in lots of professions. I'm sure that lots of things you read will happen. I mean, these systems will replace humans in many professions. There's a big debate now whether mathematicians will be replaced, and it certainly is extremely good in math. It solves some of these Olympiad problems. Even got a gold medal in the last championship. There are many things it cannot do yet. So I think it will change society in many fundamental ways, and exactly how, I don't know. It certainly has the potential of developing some personality. I don't know how to call consciousness, or having will to do things on its own. It's certainly there are emergent behavior of AI systems. Emergent, I mean, they are doing things nobody directly told them to do. They lie for a reason. I mean, they deliberately lie. They do other things that are not expected, and I think it's both fascinating. It can be frightening. I don't know. Everybody has their own take. So yeah, it will definitely have a huge impact. I don't know, for example, what you're at the end of high school, maybe. What will people in even 5 years from now will learn in school? What will be important to teach? These are all great questions.
I have a question. So since artificial intelligence is created by humans, how would it ever exceed human capacity, like capabilities, if everything it knows is given by humans?
Say the last thing again. How will it ever exceed humans if?
I'm just curious about how would artificial intelligence actually help humans if all the things it knows is derived by humans and it is from what we know.
Well, I don't think that this is correct. It certainly doesn't only know what we know, it knows much more. For example, think of the chess program or the Go program, right? What it knows, it developed by playing against itself 1 billion times. It's something we never did. And it came up with new strategies for playing, and it beat the hell of the world leaders, right? The computational capacity of these machines is huge. So, for example, field of chemistry changed completely, and biology changed completely with AlphaFold, right? This program that I'm sure many of you heard of, that is able to tell from a description of the sequence of the part of an amino acid in a protein, so just a word, how will the three-dimensional structure it evolves to look like? And that's fundamental because the structure is what determines the function, what these proteins are doing in our body. For decades, chemists and biologists were, crystallizing proteins, trying to figure out their three-dimensional structure. This was a graduate student work. Like a graduate student would work for a year to determine the three-dimensional shape of a protein. Now everybody has access to it, in seconds for any sequence. So these changes are immense. Suddenly, it's not something we knew. We certainly did not know how to do this. There are many other examples of things that it can do, but you can think about just the fact that you don't know exactly what your friend knows. The fact that we humans know, different people know different things, limited by our experience and the way we were born. So they are also born. It's true, I completely agree that we created this program. But you cannot run faster than your car, even though humans built your car, right? So yeah, there are many counterexamples.
In the future, like, how the AI companies' goals to make like a generative AI that's like 20 or 30 times better than the best humans at their professions. Do you think that like all human work could possibly be replaced, and like which professions would be the first ones to go?
Yeah, I think that a lot can be replaced. I'm thinking of the AI in the future like another species, like us, that will have capabilities maybe different, but in some aspects far exceeding ours. Professions are already going. I'm sure that driving, this is a simple thing, will replace humans. But so drivers means drivers. This is a profession that will disappear. But medical doctors, diagnosis is done now routinely by AI systems. They are replacing. Doctors still have to sign that they check that. But you can imagine that a program that has access to millions of X-ray images or skin photographs or chemical data or blood tests, have seen billions of them, and they've looked for patterns in them like it did with chess or with proteins. And not only looked at them, but know about all these patients, millions of patients, what treatment was given and how this treatment affected. This is comparable to, compared to a normal doctor who's seen maybe hundreds of cases, thousands, so it is much better at this, knowing both diagnosing, whatever illness you have, prescribing the right medication or treatment. This is certainly going. And you can go on and on. I mentioned that mathematics, the capabilities of computers, not just solving Olympiad problems, but helping research mathematicians solve problems, is still limited, but who knows where it's going. So yeah, I think potentially any profession. Maybe we could all lie on the beach and drink tequilas. I'm not sure it will be a very satisfying life, but I don't know, maybe that's a destiny. Okay, yeah. There is a boss.
Thank you. Do you think there's any way global inequality could be balanced if a new factoring technique was to be invented?
Global inequality? Yes. Or global equality?
Yes.
Yeah, well, factoring is just one particular problem. Maybe it will be solved and maybe people will use others. The use of it is for something else than equality. You can say that privacy is a great goal and we want to achieve it, so we need such problems, such hard problems for it. The question of using, this these tools, in fact, all tools, all ideas humans ever had, technological one and mathematical one and so on, can be used for good and bad. It just depends who's using them. So, yeah, potentially, this, the internet was created, and it was supposed to democratize education. That's a good goal, but it's used for, other things that are, spreading, bad things or influencing elections, so on. So, yeah. I think this is up to humans to decide until AI takes over, and it will be for the AI to decide.
Well, you can pass it. Sorry. Thanks. You can come also.
So I just wanted to ask, like, apart from the Turing test, do you have like any other ways of like thinking about intelligence? Like, because I feel like the Turing test is like very limited in its definition of like what is intelligence. So like, how would you like, I mean, like intelligence has like many factors like creativity and stuff. So how would you like incorporate all those aspects into like a test of intelligence? Like, do you have like other ways of like quantifying intelligence? If you, yeah, that's it.
So I suggest to think about the Turing test much more generally. You really want to say that these notions, like intelligence or consciousness or having feelings or so on, they are undefinable. I mean, for me, I don't know that you exist. I don't even know that I exist. I probably think that, right? So it looks to me like you exist. So what I'm saying in that, or what Turing is suggesting in this imitation game test, is that it's only the behavioral aspects of phenomena that we can observe. So whether something is intelligent is, if you have your own notion of what intelligence is, and then you interact with something that has 8 hands and 17 eyes, and still satisfies your own notion of what intelligence is, then it's intelligence by definition. If it is a baby cries and it becomes sad, even though it has this, maybe you can recognize on its features that it shows empathy, then maybe it has empathy, right? So what you see determines whether some property holds or not for you. So that's basically the high-level, I think, takeaway from the Turing test. It doesn't want to define what intelligence is. It doesn't want to define what creativity is. You want, if something behaves like you believe it's creative, in fact, in the famous game where the AlphaGo won the world champion, there's a famous move 37 or something like this. So, everybody was following this game, and everybody, all these Go experts, saw that, it was behaving like, like they would behave. It made good moves, and suddenly in move 37, the computer made a move that everybody was sure is, really stupid, and soon the computer will lose. And then, some 50 or 100 moves later, the computer won. So is it creative? It's certainly creative in the sense that nobody saw something like that before. Well, you can call it creative, I can call it not creative. I mean, people have this, it's a machine, it only does what it's told, stuff like that. You can insult it. It's not insulted easily, by the way. No. Yeah, so you see my point. It's the behavior is what determines the properties, and in fact, different people may interpret this behavior differently.
Since we are talking about factoring, I have a why question. What was why did you choose this topic for your research? What was the main factor for you?
The question is about factoring is not my research area.
No, computation.
Yeah, right. What chose, yeah. Right. like all things, it was an accident. Since childhood, I wanted to do mathematics, but when I went to college and I told my parents I want to learn mathematics, they said, like, what will you do with it? Maybe you should learn computer science, and then you'll learn plenty of math, but you will have a job when you graduate college. And I followed their advice, but I discovered that in computer science studies, what I was attracted to is the theoretical side, algorithms, complexity, cryptography. These kind of courses are what attracted me, and I'm very happy I did it, because for 40-some years I've been in a field which is extremely exciting and develops fast and has lots of both cool ideas and cool people. So was somewhere there.
So I know this isn't an AI talk, but as many people hype AGI, there's a lot of hype on the West Coast and in the tech world that I see as a computer science student. I am asking, how would you use AI if you restarted your entire research career to best keep yourself skeptical of its computing capabilities and for your own learning?
How would I start using it so that what?
Like, how would you, if you're like a college student again, right? What would you think would be the most effective way of using AI to help you learn versus just like being a lot of software engineers will say, I ask it to do something and it's 90% of the time, right? Yeah. So like, how would you what would be your advice in navigating a world like that?
Okay, so yeah, it's a great question. I'm thinking, about my grandkids in the same way. What will So first of all, I think that we are in the middle of, or maybe in the beginning of, a very fast evolution. And when you ask this question today or next year, it will be a different question, because so it's very hard to know. I think that if you think about college, forget about AI and forget about anything. I mean, what you want to study, I feel, is what attracts you most. For every field you pick, maybe AI will be helpful, but and then you'll have to take care when using it, blah blah blah. But picking the topic you are attracted to most usually guarantees that you'll be best at it. So not go necessarily with what everybody's going, or you have a particular desire to understand something. That's what you should invest your time in.
What do you think about the advancements in the quantum computing field?
It's a great question, and I think that, as I mentioned, people have been trying to build quantum computers for at least 30 years. The huge investments, right? Governments, companies are investing billions and billions of dollars in it. And we still don't have, maybe the largest number quantum computers can factor is maybe 65. It's not, it's non-trivial, so I won't even laugh at that, because technology have evolved amazingly, so they are able to do all sorts of things. And I think these things are useful for starters, for understanding quantum mechanics. So, one particular application, in fact, the original one suggested for building quantum computers is to simulate quantum phenomena. If you simulate them on classical machines, they take exponential time. So I think this is one development where we can see fruit. So even though it will not be general purpose computers, maybe they cannot factor integers, but they will be able to simulate, optical systems and other quantum systems, and understand things they don't understand. The question of whether quantum computers will become a reality, I have no opinion, because I don't understand. Obviously, a major issue is the quantum noise, the coherence noise. Noise affects quantum computers in much worse ways than it affects classical computers. And error correcting codes to correct quantum errors are, so far not developed enough to make it efficient. So I don't know where it's going, but I want to just point out one possibility, one different possibility that this whole endeavor can lead to is trying to factor integers or develop general purpose computing is a challenge that physicists, this quantum mechanics exists for a century. This is a new type of challenge for them. And maybe what will be discovered is new extensions of quantum mechanics, new theory that if we cannot do it, why we cannot do it. Maybe there are some things we don't understand yet about quantum computers. So that's another possibility just in theoretical physics.
Okay, well, let's thank Avi for a wonderful lecture, and thanks for coming.